Yes,
Hello,
I can
Ivan.
hear you if you speak louder.
Can you join us, please?
Yes, could you allow me to share the screen, please?
The answer is always yes. Just keep going and we'll do what's necessary. Yeah, we are getting your screen now. Good. I think it's happening. Yeah, thank you.
Okay, so I didn't know exactly, how the panel is imagined, so I prepared something very brief and actually, I think much more entertaining than what I told you about in my talk. So here is characterize novel quantum materials. Can you hear me? So this is a system that we put together at Yale. It's pretty unique. It contains an MBE synthesis coupled to a low energy electron microscope, which can also work as photoelectron microscope and also can provide lead. And then there is another chamber coupled by ultraflight vacuum connection to all of that, where we can do in situ cryogenic measurements of transport and magnetic properties. And that's all under UHV, so we can study reactive and air-sensitive materials. So elemental quantum 2D materials are atomically thin and covalently bonded structures formed of a single element or sometimes of a combination of elements. And indeed, the most famous example is graphene that everyone knows about. It's a honeycomb structure of carbon atoms with very strong covalent carbon-carbon bonds that provide graphene high mechanical strength and flexibility. And more interestingly, its electron band structure shows this gapless linear dispersion that makes the charge carrier effectively massless, leading to high conductivity and mobility. But to exploit these fantastic properties, one needs to be able to fabricate large area graphene. Now, borofene is an atomically thin, yes? Borofene is an atomically thin covalently bonded boron sheet. Can you hear me? Yes. It forms a triangular lattice with some vacancies, which can order in many ways. And this endows borofene with remarkable polymorphism. It can exist in many structures, which is unique for quantum 2D materials. All the others have fixed structures. Now, borofene was predicted to show anisotropic electronic transport, high metallic conductivity, optical transparency, mechanical flexibility, and superconductivity with high temperature, which could be modified by tuning the structure. But to employ these fantastic properties, one needs to master the experimental synthesis of borofene. And now comes the entertaining part. This is a movie of growth of borofene on copper 111 surface. Borofene is blue and copper is copper. So you can see that the growth largely nucleates from a step edge in the substrate, growing on the lower terrace about 5 times faster along the edge than perpendicular to it. And some of these islands can reach an area of 100 microns. However, when we have better substrate with larger terraces, then nucleation can happen in the middle of the terrace, and then the islands tend to grow triangular. For a theorist, this one movie contains a PhD thesis worth of information about surface mobility, growth energetics, etc. On the technology sides, this opens the prospect of fabricating in-plane heterostructures. Now, to decipher the structure of borofene, we carried out micro-lead measurements. These 6 lead patterns were taken from a 1.5 micron spot at different positions on the surface. The white rhomboid indicates the unit cell of the substrate, and the red and the pink are the unit cell of borofene. The 6 domain results from threefold rotation of two types of unit cells with different chirality. With the lead pattern taken from a single domain, we could decode the big unit cell, which is about 2 by 1.5 nanometers. The simulated lead pattern fully agrees with the experimental data. And to get the atomic resolution, we attached a CO molecule to the STM tip. And in that case, the PZ orbital dominates the time of the process, and the spatial resolution improves remarkably. Using this technique, we got the atomically resolved images of borophane. By DFT calculation, then we can explore all the possible models that match this STM pattern. And the most stable structure is shown here. The zigzag line pattern in the STM image originates from the chains of vacancies. So in this work, we also successfully synthesized borophane flakes that with an area reaching 100 microns square. Now, in the initial borophane studies, everyone chose 111 surface because it has the same rotational symmetry as the triangular boron lattice. However, the vacancies in borophane lower the symmetry and give rise to the formation of rotation domains. Now, surfaces with lower symmetry can favor one domain orientation and suppress the formation of domain boundaries. And moreover, incommensurate coordination between borophane and the substrate can reduce their coupling. So with this motivation, we decided to try a copper 100 surface, which has a square lattice. And we discovered that borophane can form on it. And moreover, it was a new phase, new allotrope of borophane. And so we found that the symmetry of the substrate indeed affects the structure of the borophane on top. So to summarize, we have discovered 4 borophane phases on silver 111 surfaces, 2 more on copper 111 and copper 1100. We have grown borophane on nanofilms, nanoscale thick films of copper 111 on top of sapphire, which is an insulator, which is a step towards exfoliation by sacrificing the copper buffer. And we have shown that we can grow borophane even on substrates that have different symmetry, like tetragonal symmetry. Now, what is it good for? Well, so far just for some publicity. But I want to point out that the borophane game has just started, so stay tuned for more to come. Thank you.
So, any immediate comments on this one? I have just one question, Ivan, for you. Can you hear me, Ivan?
Yes, I just want to stop
We all
sharing
know
this.
the state of the art
Okay.
of molecular epitaxy and everything you're doing. Can you hear me?
Yes.
There'll be additional discussions on other methods. Is there any other method apart from this one that you just now mentioned that is now of great interest to you, in your view?
Yes, actually. Okay, so our method is very expensive and
Yes.
slow. It is great for exploring the phase diagram because we can do it in one day. We can watch by limb and the morphology, the growth of the islands. By lead, we can watch the crystal structure, but this is not practical as a manufacturing method if you want to go to the wafer scale and mass production. But there are some groups that are pushing CVD, and with some success, they use borazane as a precursor, and that certainly looks like much cheaper and more scalable technique. It will take, it takes chemists some time, some years to develop the alternative to physical vapor deposition methods. But once they do, you are out of business. Then they can do it much cheaper and much better and on a bigger scale. So CVD is worth looking, and I would say also ALD. So far there was nothing, but I would hope that in the future we will see some of that as well.